When you stand up a new application today, the pressure to get the database right is immense. You are making a permanent bet on how your data will live, breathe, and survive scale. By 2026, the lines between our top two contenders have blurred. Postgres deeply integrated JSON-B, allowing it to handle flexible documents. Meanwhile, MongoDB adopted multi-document ACID transactions, pushing it into traditional database territory. We used to draw a hard line, relational tables on one side, NoSQL document stores on the other. Today, those old labels fail to capture what either system can actually do. Because both databases check the exact same boxes on a feature list, you can't rely on a simple side-by-side comparison. You have to look under the hood at the underlying core engines. Choosing between Postgres and MongoDB requires a commitment to a specific way of handling data mutation, integrity guarantees, and scaling at the engine level. Many early-stage development teams default to MongoDB to get their prototypes out the door as fast as possible. Its schemaless document architecture allows developers to throw data at the database without defining a rigid structure upfront. You can ship new features on the fly without writing tedious database migrations. As the application matures, those early speed gains often convert into a maintenance burden. Teams begin dealing with data duplication across documents and finding resources that weren't cleaned up correctly after a delete. Without relational safeguards like a cascading delete, which automatically scrubs connected data across tables, your database begins to fill up with orphaned records. To maintain order, engineering teams end up building complex schema validation entirely within their application code layer, rather than letting the database engine enforce the rules natively. Optimizing exclusively for development velocity creates a high maintenance cost once an application's data becomes inherently relational. To understand how these databases truly differ, we have to look at concurrency, how each system handles simultaneous updates to the exact same piece of data. MongoDB uses document-level concurrency control. Its engine relies on optimistic conflict handling, which allows it to push through extremely high throughput when you are only mutating small, partial sections of a document. Postgres treats JSON differently. If you update a single nested field inside a JSON-B column, Postgres locks the row and rewrites the entire record. Every time that row is rewritten, it gets recorded in the write-ahead log. If your app makes frequent, tiny updates to massive JSON documents, you trigger heavy write amplification, which drags down performance over time. This chart shows read and write times across varying dataset sizes. While read times are comparable, Postgres write times increase significantly compared to MongoDB as datasets reach the large mark. That scale also impacts hardware resources, specifically processor strain under heavy load. This graph tracks CPU utilization. At the large dataset mark, the two systems diverge sharply, with Postgres requiring significantly more processor overhead to handle the workload. MongoDB holds a clear structural advantage for mutation-heavy document workloads. Postgres consciously sacrifices that raw write speed to guarantee absolute ACID compliance across mixed data types. Beyond raw update speeds, we have to look at how each system manages sudden traffic spikes and long-term user growth. MongoDB relies on a native horizontal sharding architecture. It automatically distributes heavy write loads across multiple servers, splitting the traffic so no single machine gets overwhelmed.
But native sharding carries hidden operational complexity. It requires intense engineering effort to choose the correct shard keys and manage chunk migrations without creating bottlenecks. Postgres defaults to a simpler strategy. It relies on vertical scaling, adding hardware to a single machine paired with read replicas. By separating heavy write operations like processing a checkout from lighter read operations like browsing an item catalog, a Postgres read replica setup can comfortably survive massive e-commerce traffic events. There is a strict ceiling on Postgres's single-node write throughput. If you need true horizontal scale for incoming data, you have to lean on third-party extensions. MongoDB can scale writes horizontally from day one, but it requires massive operational overhead. For teams lacking dedicated DevOps resources, Postgres's simpler read replica model is a safer bet. Eventually, many scaling SaaS teams drowning in data integrity issues decide they need to move their data entirely from MongoDB to PostgreSQL. The harsh reality of any migration is that absolute zero downtime is nearly impossible. You have to implement a read-only write freeze to ensure total data integrity while the transfer happens. Step 1 is planning the schema. This means taking your embedded NoSQL documents and aggressively converting them into strict, normalized relational tables. Step 2 is scheduling and strictly enforcing that brief application write freeze. Step 3 involves utilizing a persistent key-value store to accurately map legacy MongoDB object IDs over to new PostgreSQL UUIDs. Doing this ensures you don't run out of memory during the heavy data transfer. Step 4 is the mechanical execution. You move the transformed data, table by table, into the new database. Step 5 is validation. You confirm the data matches perfectly, switch the DNS, and finally, you resume normal write operations across the application. Executing a total database migration is a high-risk operational trauma. It is only justified when the compounding daily cost of tech debt and manual cleanup in MongoDB outweighs the pain of the move. At this point, we need to shift our evaluation away from technical benchmarks and look closely at the total cost of ownership. The true cost of your database is rarely software licensing. It is the human payroll spent on schema migrations, on-call fatigue, and compliance auditing. To make the right choice, map your specific business needs against capabilities. We plot relational complexity on the y-axis and write-scale needs on the x-axis. MongoDB dominates the quadrant requiring massive horizontal write-scale but low relational complexity. PostgreSQL dominates the quadrant requiring high relational complexity and moderate write-scale. Achieving maximum return on your engineering investment requires matching the database's architectural assumptions directly to your specific market segment. If you are an architect starting a brand new application from scratch today, the decision process is clear. PostgreSQL is the undisputed safer default for modern web applications. Its hybrid data flexibility, combined with strict structural guarantees, covers the vast majority of use cases. You should only pivot to MongoDB if horizontal write sharding and fine-grained mutations of document-shaped data are mandatory requirements on day one. Success depends on choosing the database whose internal trade-offs support the application's long-term survival, well after